Well, hello friends. Welcome back to OS Hacking. Today we're going to implement a technique that I heard about in Linux. So apparently they have this thing that they call a read-only after init memory. And it's a technique where they identify data in the kernel that only needs to be written during the initial boot process. And then once the system is up and running, they never want to write to that data again. And what you can do with that information is that you can collect all of those things in one place, and then once the system is booted, you can make all that memory read-only. And I thought this sounded like a fantastic mechanism that we could also implement, right? And that's what we're going to do today. So basically, the first thing I had in mind for this was our IDT, which is our x86 interrupt descriptor table, because once the system has booted, we never want to change any of the entries in the IDT, but it is currently in it's just in the kernel data section, right? So it's just writable kernel memory. So that's sort of the first target, but then really any global variable, for example, that we never want to write to again after the system has booted is a good candidate for this kind of thing. So I think what we're going to do is we're going to put these in their own section first off. So like RO after init, something like that. I'm missing a paren. And actually, let's make this a macro. Read only after init. And then, yeah, so then you can just put this in front of anything. So we'll do both the descriptor table pointer and the IDT itself. And probably we can move this up to somewhere higher. Yeah. And we probably have various things like in various places in the kernel, like here, like the TTY0, the first TTY pointer. Once we have actually created TTY0, we never need to write to this pointer again. The fact that the pointer is writable, you could argue, is a little bit of a security hole. Like any writable memory could be thought of as a security hole if it doesn't need to be writable. So this is just a way that we can tighten things up. So the trick now, of course, is to how do we actually make these variables read-only after init? So now that we have this attribute on them, it means that we're going to put them in their own elf section. So we'll recompile the kernel, and then we'll take a look at the elf sections. So if we look at the sections in the kernel, we can now see that we have a brand new RO after init progbits section. So this is just a section containing all of the variables that I just marked with that attribute, and it has hex 80C bytes in it already. So I guess like just over 2 kilobytes of stuff. And by itself, this is not super useful, but if we go and look at the linker script of the kernel, we could actually put these things into their own section. So let's see. I guess what we'll do is something here, like we will align them so that they're 4 kilobyte aligned, because we want it to be aligned on a page boundary, because that means that we know that like we're not mixing it with any other data, so nothing else that shouldn't become read-only becomes read-only. And then here we will simply say RO after init, and let's put a marker here also, and a marker after, and these two markers we'll be able to access them from C++ so that we know where the section begins and ends. And then at runtime, we can actually go and update the page tables for only this section. So we kind of do some stuff like that already for making the data of the kernel non-executable in memory manager somewhere. Let's see, NX somewhere. Yeah. So we have memory manager protect kernel image, which we run after booting up. Once we have paging and protection and everything up and running, then we go and we mark all of the text and read-only data segments as non-writable, and we also mark the data, BSS, and heap segments as non-executable. So I think we're going to do something similar here, but we're going to make we're going to disable writing to the RO data, RO after init section, but we'll do this a bit later. So we'll put it in its own thing. So protect RO after init memory. Read only, yeah. Okay, and then since we have those markers, we can just say start of RO after init and end of RO after init, but of course we also have to just extern them here so that C++ is aware that they exist. Start of RO after init. End of RO after init. Okay. And then when do we call this thing? So first off, we need to actually call it from somewhere. We need to what am I thinking? we need to add it to the memory manager header first of all. Okay, and then we want to be calling this puppy from init in the kernel. So when is a good time to do this? Like, should we do this right before we start the scheduler? Or we can do it even a little bit later. It seems to me that it's okay to delay this until maybe like until we launch system server, because that's like when the kernel init actually kind of ends and the user space init takes over. So I think we'll do that. So we have init stage 2, which is the multitasking part of initialization. We're still creating devices and stuff here, so I think it's okay to let that keep going. But then let's see. So here is where we launch system server. So maybe here, after we load the kernel symbol table, then we will say memory manager protect read-only after init memory. Like that. Note. Oops. Read-only after init. Everything marked read-only after init becomes non-writable after this point. Yes. Okay. So let's see if it boots with this change, because it is very possible that we will actually try to write to some of these things. But I don't think we should. So let's figure out what actually happens if we try to boot. Okay. We have, we need to be holding some lock in protect read-only after init memory. Sure, we can do that. Scoped spin loc, the SMM lock, sure. that's fine. Okay. So it was a little too easy. I wonder if it actually worked. So let's print out the addresses here that we are actually marking as non-writable. So the message line. We'll just do something simple like this, right? Like just print out the address. So did we print something? Arrow after init. Okay, this address right here. All right, fair enough. So I guess if something were to try to write to these things, let's see what happens if we try to do that. So we have to, I guess we can just go, so we marked TTY0 here as read-only after init. So let's try to write to it, actually. What happens if we just try to set it to null, right? Boom. Kernel panic. Crash in ring 0. Oh, wait. So I'm just assigning null footer to it and then dereferencing it. So I'm not sure that this actually worked. Let's see. Message line. Let's print out the address. Let's print out the address of TTY0 and see. And let's make something that we don't need to use. So we make something like, I don't know, foobar. And then let's assign to it. So like foobar is 3. Okay, so everything actually boots. So TTY0 is inside of that thing. So arrow after init, I feel like that's not taking effect. Why is that? Oh, wait. We need to actually flush the TLB for that address. Otherwise, this the CPU is not going to care. So TLB. How about we just flush the entire TLB after we're done with this? I would have thought we would do that normally. I guess it's better to only flush that address. So what are the arguments then? Page directory and virtual address. Sure. So like that. Okay, so now we do get a kernel panic. Great. So we were just missing a TLB flush. That is cool. And then we have fault at an invalid address. Sure. So it would be super neat if the crash message could even tell us that, like, hey, this is, you're writing to arrow after init memory, right? So let's teach the crash message thingy about that. So where would that be? We want to be at essentially where this message is coming from. Pagefault. we? Handle page fault. Here is where we would be, because there's no corresponding region for this. So we could do something earlier, actually. Before we call memory manager, we can do this directly in the page fault handler. Oh, we need that range information. Start of row after init. So let's put those here. And then wait. I think. Why does this code look so weird? Oh, wait, it doesn't look weird. I just assumed this was, I thought this was like this, but it's not. Okay, never mind. So, before calling we will simply check if fault address is within the RO after init section. Then we can panic. Write, attempt to write into RO read-only after init section. Yeah. So that would be a very helpful error message, I think. Undefined reference to, oh, wait, I need to put them outside of the kernel namespace. Okay. Kernel panic, sure. But we're seeing a crash in ring 0. Page fault in ring 0. Oh, wait. I have to take the address of these things. Yeah, that's how we get them. Okay, so finally, attempt to write into read-only after init section. That's excellent. And then it tells you exactly where this happens. So at CPU CPP 272, we are panicking. Oh, right, yeah, but I guess it would be best if we would show the actual fault location as well. So we should really dump before panicking. Okay, so kernel panic, and then here you get to see what actually happened, right? So if you take this, you learn that it's at init CPP 306. Yes, assigning to foobar. Okay, so it works. Cool. Okay, so that was a little bit messy, but we got it working. So basically, now, let's just get rid of that foobar thing. So now we have a way to decorate any variable in the kernel with this special attribute. And then once we call protect read-only after init, then these variables will no longer be writable. So I think that is very, very interesting. So let's find something else to put it on, like the scheduler, for example. We could put this on like a bunch of things here, I guess, like the finalizer thread. Once we create the finalizer thread, you're never gonna write to that variable. Just read. Same thing here. We're not gonna overwrite this. We're not gonna overwrite this pointer. The ready queues, we're not gonna overwrite those, I think. Yeah. I think we would only ever write to this in initialize. Yeah. Okay, and I'm sure we can find some more things. Let's see if it works with these ones we just put. Yeah, it still boots. That's cool. So if we look in kernel process, CPP, so we can find some stuff here, like this one is, read only after init. The global process table, we never need to overwrite that pointer. That would be a problem if somebody did. So let's make all of these read only after init. This is super neato. Yeah, I'm not gonna like comb through everything right now, but we'll take these obvious ones that we just that we can just see. And I think that's pretty neat. I wonder how big that section ended up now. So wait, where did it even go? Oh, I guess it got merged into the BSS because I told the linker to do that. So we could probably make its own thing. So something like this. Yeah, so now we can see it as its own section here. And it's 834 hex. So 2,100 bytes of stuff. Yeah, and then, as I said, we should just like look around and see if we can find more stuff like this. And of course, this is only one way of doing it. So now we're only doing it to globals, right? Like kernel data variables that are just sitting around in the global scope. But we could also imagine doing the same thing for something more dynamically allocated. So you could imagine having a dynamic allocator that gives you memory, and then at some point you tell it, okay, so all that memory that you gave me, now make it read-only. Because we have a lot of dynamically allocated stuff as well. So that would be an interesting expansion of this concept. But just as a start, I think this is really neat. And I'm particularly happy that we can protect the interrupt descriptor table this way, because if you were to get write access to the kernel, then you could certainly create a lot of trouble by writing into the IDT, and now that is at least write protected. So you would have to gain enough control to unwrite protected, which would be, I guess, more difficult. So yeah, very neat, very neat. And this doesn't feel like it costs us that much complexity. Like if something is ambiguous, like whether or not it should be read-only after init, we can just let it be writable. So we'll see how this works out. But I think this is a very cool mechanism. So I'm glad that we are implementing it. So let's commit some stuff. So I guess we'll start with just the macro and the linker changes and the stuff that actually makes it non-writable. Okay, kernel. Add a mechanism to mark variables, to make some variables read only after init. After boot, something like that. Memory, let's say. Okay, so you can now use the read only after init macro when declaring a variable, and we will put it in a special arrow after init section in the kernel. All the memory pages in that section will then be marked read-only, or data in that section remains writable during the boot and init process, and is later marked, or is then marked read-only just before passing control to system server, just before launching the system server. This is based on a concept from, based on an idea from the Linux kernel. Yes. So I don't know what they call it exactly over there. I just heard about it in a talk by Case Cook, but this was sort of my understanding of the concept. So I hope I understood it correctly. But even either way, like this seems like a very reasonable thing to be doing. So kernel. Mark a bunch of things, or you know what? Let's make this bisect friendly. Oh, and we should have that panic thing here. Kernel. Print a helpful panic message if crashing due to read-only after init. Yes. And this part should be in that commit as well, I realized. Okay. Mark the x86 IDT as read-only after init. We never need to modify the interrupt descriptor table after init after finishing initialization. So let's make it an error to do so. Indeed. Mark a handful of things in process, CPP, read only after init. Yeah, we'll just do this. These will be unexciting messages, but wait, why didn't I combine those? Okay, and thread CPP. Oops. I'm just doing it this way so that if we're bisecting this, then we'll find them quickly. CPP as read-only after init, sure. I'm surprised that we didn't have more stuff here that could be read-only after init. I mean, there probably is a whole bunch of things. It's just also a lot of stuff that could make use of this pattern, but would need to be split apart a little bit, like per CPU data. Like once we have booted all the CPUs, for example, then we could mark some of their data as read-only after init. S-apic. Yeah, so like you could do like that, right? Anyway, I'm not going to sit here and go through everything, so I think this was sufficient for what we wanted to do here, and we'll continue to do mark more stuff as read-only after init, but it's a cool start, I think, and you can see that we can still browse the web. Still works. That's good. Yeah, so I think this will be the end of the video. So if you made it this far, then I thank you for watching, for hanging out, and I hope that you saw something interesting here. I think this was a pretty neat little mechanism, and it turned out pretty good. So it's just yet another thing that we do to make the system a little more robust, a little more resistant to attacks, because that just never ends. Like, the game goes on. So anyway, thanks for checking it out, and I will see you next time.